The other way that we express concentration very commonly in chemistry is with molarity. And molarity, or that capital M, is just how many moles of solute we've dissolved per liter of solution. Okay? So seeing that capital M can always be replaced with moles per liter. So if we saw 5.0 molar, that means just the same thing as 5.0, 5.0 moles per liter. Okay? It does not mean 5.0 m per liter. That m does not mean moles. That m means moles per liter. Okay? It means the fraction. So please keep those separate from each other. Right? It's related to moles, but it's how many moles have dissolved per liter of solution. So anytime you're to calculate the molarity of a solution, we're going to have to ultimately do moles per liter. Okay? When you're calculating a molarity, what is the molarity? You're going to have to do a moles divided by liters. Okay? But we're not given moles, we're given grams. So we have a little work to do first. We have to convert those 14.2 grams of NaCl into moles. So we'll use the molar mass. I've added Na and Cl up from the periodic table, 58.44 grams. That's per 1 mole. So the number I get there is 0.24298 moles of NaCl. Okay, so that'll ultimately go on the top of our fraction there. The other thing we'll need to divide that by is liters. Well, we got milliliters, so we're close. 250 milliliters. All we have to do is say that there are 1,000 milliliters per liter. Okay, and that's just the same as moving the decimal point over. 0.250 liters of solution. So finally, what we have to do, right, molarity is moles, in this case, NaCl, divided by liters of SOLN is solution. Okay? So for us, it's going to be the 0.24298 moles divided by the 0.250 liters of solution, moles of NaCl. The number I got right here is 0.972, and if we just took those units, it would be moles per liter. But remember, moles per liter is the same as that m, so 0.972 molar. Okay. When you ask what is the molarity of that solution, that's what we're talking about. So whenever you have to calculate the molarity, it's going to be moles per liter. If you're not given moles and liters, you have to do conversions. We did something very similar to this with density at the beginning of the semester. So if you're not given the right units, you have to convert them first. Another common thing that we'll have to do is to be given a molarity as part of a problem. And just like when we had a percent, if you're given a molarity in the problem, you use it as a conversion factor. So what mass of sodium chloride solid is required to make 250 milliliters of a 3.5 molar NaCl solution? What we have to remember is that molarity is a conversion factor between moles and liters, right? It'll go from one way or another, right? Because molarity itself is moles per liter. That's what its definition is. So if I've got a question like this, I need to end up in grams. I need to start in milliliters just based on what we're given, right? Because we're going to be converting moles through moles and liters there. Those milliliters have to go into liters. That's just by a factor of 1,000. liters now can be converted into moles using the molarity, right? Using your moles per liter as a conversion factor. In fact, I'm going to write moles per liter right there. And then we can use the molar mass to get that into grams. Okay, so anytime we're dissolving a solid like this, it's just a matter of unit conversion, going from the volume that we need ultimately into the mass of the solute. Okay? What is key here is to understand that 3.5 molar means 3.5 moles per liter, so that when we set up a fraction of that, it's 3.5 moles per 1 liter. Right? And it's going to be 3.5 moles of the stuff we're dissolving, in this case NaCl, per 1 liter of solution. And that fraction can be inverted if we need to, depending on how we cancel those units. So what we'll actually do here is take 250 milliliters of solution, say that there are 1,000 milliliters in a liter. Okay, that got us right here. Now I need to use moles per liter, right? 1 liter of solution contains 3.5 mol. Okay. This entire fraction right here came from the fact that we were given 3.5 molar NaCl in the problem, okay? This M means moles per liter, so that M never shows up in a conversion factor, right? That's never a unit that we cancel, because that M itself means moles of one thing per 1 liter of the solution, okay? So if you can understand this, 3.5 M becomes that conversion factor, then I think you'll be in good shape here. All right, the molar mass, 1 mole of NaCl contains 58.44 grams, just from the periodic table. The answer I would get for this, just from those rounding from those 2 sig figs, would be 51 grams of NaCl. That's the mass of sodium chloride required to make 250 milliliters of sodium chloride solution with this concentration. We used that 3.5 molar as a conversion factor, right, as we were canceling our units. Cancel liters of solution there, moles, things like that, and we'll end up with grams of NaCl. To actually do that, to actually prepare a solution by dissolving the solid, we have to do that calculation that we did, right? Figure out how much solid we want. We're going to measure it out, and we're going to add it into a volumetric flask of the correct size. So in our example on the last page, we need to have a 250 milliliter volumetric flask, because that's how much solution we need. Okay, so what we're going to do, we're going to measure out that 51 grams of NaCl. Let's pretend there it is, 51 grams of NaCl. We're going to dissolve that solid in water. Okay, you do this in the lab. You're going to just add some water to get it dissolved first. Okay, then it's totally dissolved. This is the water. And then finally, we need to add the remaining water to the line on the volumetric flask. Okay, so we're going to very carefully add it so that the bottom of the meniscus is right there at the line, which represents the particular volume that we're going for. Okay, so our problem said we need 250 milliliters of this solution, so we need to get a volumetric flask that is marked at 250 milliliters. And we use a volumetric flask like this because this makes a total volume of solution. We will never be calculating how much water we add because that's not a direct additive relationship. Even with liquids, okay, 10 milliliters of one liquid plus 10 milliliters of another liquid does not make 20 milliliters of solution. Okay? So we're never going to calculate exactly how much water we're adding. All we're interested in is using a volumetric flask to make the correct total volume of solution at the end. Okay? And that's also the reason we dissolved it first. The volume changes a bit as it dissolves, so we want to make sure it's totally dissolved first, and then we add water so that our total solution volume, right, to make the correct total solution volume. Okay. That's the way that solutions are properly made. Okay. We don't talk about adding this much of this to adding that much of that. We talk about precisely measuring out usually the mass of solute and then adding however much water we need in order to make the correct volume of the solution total. Okay. So here's a new problem right here. I want to make 1.5 liters of a solution, 2.75 molar copper nitrate, right, by dissolving a solid. What I'd like you to do now is pause me and see if you can start with, see if you can do this. It's going to be a unit cancellation, just a lot like we did before. Okay, a couple of cautions here. Don't start a unit conversion with a molarity. Okay, that certain number molar concentration becomes that same number of moles per 1 liter of solution. And you'll use that as a fraction, right? This will come from the problem here, but you use this as a fraction to cancel out units, okay? So pause me now, see if you can do this and get an answer, and then press play again and I'll write it out. All right, so I would start with the volume that we're given. We don't need to go milliliters to liters. We're already in liters, right? 2.75 molar means 2.75 moles of CuNO3 per 1 liter of solution. And then we just need the molar mass, 187.57 grams. Just add those up. That's per 1 mole. Okay. Our units have canceled. Moles. Answer I got was 770 grams. I had to round it to the 2 sig figs, so it'd have to be 770. Equally correct, I guess, would be 7.7 times 10 to the 2 grams. Copper 2 nitrate. In order to prepare that solution, we need to measure out 770 grams of copper 2 nitrate into a 1.5 liter volumetric flask. Dissolve it. Then add water, add enough water to make 1.5 liters of solution total. Okay. This last one down here uses the exact same principle. You're given a value, you're given a molarity, which becomes a conversion factor, but it sort of goes the other way. So why don't you see if you can do this? See if you can start out with 2.87 grams of CaCl2, calcium chloride. See if you can set up a unit conversion that looks like that to ultimately get milliliters of solution. Right, we've got that many grams of the solid. I need it to be this concentration. How many milliliters of that solution can we make? So try it just canceling units. So try pausing me here and see how far you can get. See if you can get an answer, and then I'll show you how to do it. I would convert grams into moles. This is its molar mass. That's grams per 1 mole. Our molarity, 0.85 molar, means there are 0.85 moles of calcium chloride dissolved in 1 liter of solution. Okay? This molarity has become this entire fraction right here. Notice I did not put an M, a capital M, in there, because that capital M itself means 0.85 moles per liter. And then, since I asked for milliliters, it's just a matter of saying 1 liter contains 1,000 milliliters, right? So you'll multiply by 1,000 at the end there. The answer I get is 30 milliliters of solution, or if you want to do scientific, 3.0 times 10 to the 1. Okay. So anytime you are given a molarity, okay, and especially if your problem involves some kind of solid here that you're dissolving out, you're going to use that molarity as a conversion factor between moles of the stuff that's being dissolved and liters of the solution. And from there, it's just a matter of getting units to cancel, right? Just like that.